Hello, everyone. This talk was given at APS March 2021, which was done virtually, and I'm recording this talk later for anyone's viewing. Thank you for watching. So I'm presenting my work at BYU at the Tree Soft Matter Theory Group on the GPU accelerated Wang-Landau simulation of polymer crystallization. This work was done with a lot of colleagues, a bunch of undergraduates, and my advisor, Dr. Douglas Tree. So we really think the problem here is best characterized by observations which are deviant from classical models. And this is exemplified by the example of melt memory. So you see a schematic in front of you of this experiment. Essentially, if you have a melt and you quench it to a crystallization temperature and you wait for it to completely crystallize, and then you take 4 different samples, or they're the same sample, from this completely crystallized polymer melt, and you anneal them at 4 different melting temperatures, as you see in front of you, Tm, with the different colors. And then if you take those 4 samples and you recrystallize them, or you quench them back to a crystallization temperature, what one might expect here is that we would see 4 of the same morphology, the same looking crystals, in other words. For example, if we look at a simple molecule like water, if you take water or ice out of the freezer and you melt it at 4 different temperatures and you put it back in the freezer, you would expect to find the same morphology of ice upon taking that ice back out of the freezer. But this is not what we see here. Essentially, for the 4 different temperatures, we see varying levels of spherolytic domain. So at the highest melting temperature here, you see from this photograph, you see spherolytic domains, as one might expect with a system like this. But then as the temperature is decreased, those spherolytic domains begin to disappear, especially with the 117 degrees Celsius sample. We don't see any spherolites there. And this is this problem that you see in front of you is indicative of deviations from classical models, but there are other observations that we believe show the same kind of behavior, like intermediate phase observations and initial larger scale ordering and Saxon wax measurements. So why is this happening? Is this a matter of slow kinetics that is maybe causing our system to evolve differently and giving rise to these different frozen morphologies? Or is it some sort of thermodynamic phenomena that is playing a role here in causing the differences in morphology based on different melting temperatures? So if we look at a free energy diagram, we could kind of see what the different possibilities are. With scenario 1 here, we see a free energy diagram that is of an activated process. You have a metastable melt below its melting point. Essentially what that means is that crystalline phase is the stable phase, and obviously the one with the lower free energy. And because this is an activated process, there will be an induction time before which a crystalline nuclei comes about that has enough energy to overcome the energy barrier and go to the stable crystalline morphology. Now, there's another scenario here where we can talk about where there's a thermodynamically intermediate phase in between the crystal and the melt that mediates that process. So the melt has an easier path to transform to the intermediate phase before going to the crystal, and then the intermediate phase transforms to the crystalline lamellae. Now, is it scenario 1 or scenario 2, or perhaps a combination of the 2 or other scenarios? And the mission here really in our project, what we set out to do is to characterize transitions using simulations to better understand the process of nucleation. And we think that Monte Carlo methods can do a good job at building this free energy profile and helping us understand our transitions. We're going to use Wang-Landau Monte Carlo because it allows us to use bond-breaking moves. Since it's a Monte Carlo process where we can break dynamic considerations, we don't have to worry about entanglements relaxation modes and other things like that that one might have to worry about with a more conventional method like molecular dynamics. It's faster and simpler. We have found a way to make it massively parallel, and it gives us direct access to free energy information, which essentially is going to help us, aid us in characterizing our transitions. Essentially, what Wang-Landau does is it helps us build the density of states of a system. So in the schematic you see in front of you, you have the real density of states for a system. In Wang-Landau, what we do, now this density of states could be used to build all sorts of profiles that could aid us in characterizing our transitions. Now in a Wang-Landau simulation, what happens is you bin the energy space in a discrete fashion as you see in front of you, and you set at iteration 0 an initial guess of 1 for all densities of states. And essentially, as time progresses and you converge your simulation with more and more iterations, you begin to approach the real density of states. And finally, at an iteration 26, the system usually converges with good enough error estimates. So that's what we intend to do. So we've used our Wang-Landau code to characterize the transitions of a single polymer chain. So we've built the density of states, and then we can use that density of states to build the heat capacity profile. Now, this heat capacity profile has all sorts of information about the transitions of the system, and it's characterized by the peaks. So the first peak on the left here characterizes the transition from a crystalline state to a globule-like state. And then the transition to the right with the red peak or the red square characterizes the transition from a globule to the coil. And essentially, what this gives us is it defines points on a hypothetical phase diagram for the level of the order parameter used for that simulation. And then we can use multiple Wang-Landau simulations at different levels of order parameters to build this phase diagram and effectively characterize the transitions in our system. But this is easy now. So we wanted to move to a bigger melt, one that is more dense, and of course not an isolated crystal. So we need to do that. We need to have a faster, more efficient simulation so we can overcome the slow equilibration that comes with a dense and big system. So we've utilized GPU acceleration to achieve faster speedups, and we found, thankfully, or we were happy to find that our simulation could effectively simulate chains 2 orders of magnitude faster than our serial code. And this was a method adapted to polymers from Anderson et al. At the University of Michigan. And we've also employed a complex polymer moveset that allows us to relax our system quicker and more efficiently. So for example, here you see 2 bond breaking moves like end bridging, which happens in with one chain where you break the bonds of the end and you reattach it somewhere else. With a double bridging move, this is it's a better example of why this works so well for our system. You have 2 entangled chains that are entangled along a bond, and if you pick those beads and you break their bonds and you reattach them to the other chains, what happens is those chains can easily move apart now, and you've effectively relaxed the system much faster than you would with conventional moveset. And we're also using configurational bias moves to speed up these simulations and increase the acceptance rates of these moves. So although we were able to bring our autocorrelation times to a low level and effectively simulate our process in reasonable times, when we went to the 2000 chain 100 bead melt, what we found, what we're disappointed to find, is that a lot of our simulations took a very long time to converge, especially when it came to the lowest energy states, where even 42 days was not enough to simulate our process, as you can see by the bars that are in red here. So we were pretty confused by this, and we went to the literature to see what other people may have done in this domain. And we found this excellent paper by Shakarov and Paul in 2018 that simulated a far smaller system than ours. And they claimed that their system spanned 5,600 orders of magnitude in terms of the entropy. And when we went and applied the same scaling arguments to our system, we found that our system spanned 200,000 orders of magnitude. And as you can imagine, we have bit on more than we can chew, and the system is going to be quite impossible to simulate effectively, even with the 2 orders of magnitude speed up that we were able to achieve. So to conclude here, we have built a GPU accelerated Wang-Landau Monte Carlo code with domain decomposition and an advanced polymer moveset to effectively simulate a polymer, a large polymer melt, and we were able to achieve high enough speedups or high speedups that we thought would allow us to access our system. But what we learned is that there are far too many orders of magnitude to resolve in our density of states, and what we plan to do in the future is to simulate a specific process along a certain order parameter versus the entire density of states of the system. And we have some sneak peeks here that we hope to get out some papers on pretty soon, where we have built the free energy surface directly using order parameter Wang-Landau, which is a method we've adapted and developed. And as you can see here with the diagram below, you see a free energy diagram versus an order parameter called Q6, which characterizes crystallization in simulation. And we plan to use this to characterize our transitions and investigate small nuclei in the future. Thanks for coming to my talk. I'd like to acknowledge my team, the Tree Soft Matter Theory Group at BYU, and my advisor, Dr. Tree, and the ACS Petroleum Research Fund, the BYU Board of Trustees, and computational support by the Office of Research Computing at BYU. Thank you.